So it's our first talk of the afternoon session, and it's my pleasure to introduce to you Professor Young-Hoon from KIAS. So, he's going to talk to us about counting sheaves in algebraic geometry. Please go ahead, Professor.
Thank you very much for the introduction. I'd like to thank Professor Seong for the invitation and taking good care of us here during this workshop. So when I got the invitation email first, I didn't know what to say because I couldn't understand the word about field theory with 8 supercharges. I have no idea what supercharges are. I have no idea what field theory means. There were symplectic singularities in the title, but I haven't thought about symplectic singularities for more than 10 years. So I didn't know what to say. But anyway, I decided to come because I wanted to learn from this workshop. I don't have much to say today, but let's see. So I'll talk about something. So recently I've been working on, during the past 10 years, I've been working on the Gromov-Witten theory, Donaldson-Thomas theory, and Van-Jarvis Rowan-Witten theory. Nowadays I'm working on 4-dimensional Donaldson-Thomas theory. So maybe I can connect these stories with symplectic singularities. Okay, so as I said, I don't have much to say, so I will speak slowly and interrupt me anytime. Okay, so let's start with the surface case. Let's say S is a smooth projective surface over complex number field. And as in Dr. Yamagishi's talk, we fix an amplified bundle, which is general. Yeah. And then let's say M is the moduli space of Fourier sheaves on S. Okay, and the slogan for this workshop is that by the work of Mukai, the fundamental work of Mukai in 1980s, if S is symplectic, then the moduli space M inherits not the whole moduli space, but the moduli space of stable sheaves, this open part in M. This is smooth manifold, and this guy is also symplectic. So this is the mantra or slogan for this area. Symplectic means S is either a K3 or abelian. And you know what symplectic varieties, like smooth symplectic varieties are. I think everybody knows here. So we have Gromov-2 form. Is non-degenerate, which gives us an isomorphism between the tangent bundle and the cotangent bundle. Right. And basically, as we have seen in the morning in Dr. Yamagishi's talk, basically all known compact examples of irreducible homomorphic symplectic varieties arise from this moduli space, from Mukai's theorem, except 2 examples by grades. Okay, so because O'Grady's example come from singularities, let me talk about O'Grady's examples a little bit more. So when stability is not equal to semi-stability, when there is a strictly semi-stable sheaf, then the moduli space of semi-stable sheaves on symplectic surface S. This is a singular projective scheme by geometric invariant theory by the work of Maruyama, Issachar, and Simpson. So I don't like dealing with general case. I usually like to deal with the simplest possible case. So let's think about the case of rank 2 sheaves, first chunk class 0, second chunk class n. So n is an integer. So in this guy can have possibly two singular strata. The open dense part of stable sheaves is smooth. And then we have the locus sigma of rank 2 sheaves, which are direct sums of rank 1 sheaves. Okay, and we have sigma here. And then inside sigma, we have omega, which is the locus of direct sum of rank 1 sheaf with itself. So sigma minus omega, this joint union, omega. So we have this stratification of moduli space. And so when n is odd, these singular strata are empty sets. When n is even, we have these singular strata. And furthermore, we know the singularity types of along these strata. They're all symplectic quotients. So singularity along sigma minus omega is something like C2G, CG plus CG, symplectic quotient by C star, weight 1 minus 1. And singularity along omega is like CG tensor, Lie algebra SL2, symplectic quotient, 2G by SL2. So we know very explicitly how it looks along the strata. We understand very well the singularity of the moduli spaces. So we can think about the Kerwan's partial desingularization process. Kerwan's desingularization process in this case is very simple. We blow up sorry? Two cases. Minimal with a very big. Probably. It's very explicit thing. Cotangent bundle of SPI to SL2 and C by G copies of and G copies of cotangent bundle of SL2, symplectic quotient by SL2.
So the dimension is
yeah. 6G minus 6 something like that.
6G minus.
Yes. So this G and this G may not be the same. Okay. So what we do is we blow up along the most singular stratum, deepest stratum, sigma, and then we blow up along the proper transform blow up along omega and then proper transform of sigma. After these two blow-ups, the moduli space MSS becomes an orbifold. You only have Z2 quotient singularities. And so by finally blowing up along this Z2 quotient singular locus, we obtain an honest resolution of singularities. Okay, so and a little later, in late 90s, Brady analyzed this blow-up process very carefully, and then he could prove that you can blow down and head twice. still non-singular, so you get another resolution of singularities of MSS. It's smaller resolution. Okay, so and furthermore, O'Grady proved that for smallest dimensional singular moduli spaces, M tilde turns out to be symplectic, smooth symplectic. So the symplectic resolution of the singular moduli space MSS, this gives us two exotic new examples of O'Grady's two new examples of reducible homomorphic symplectic varieties. So definition was already introduced from Alicia's talk. Right. And then O'Grady asked this question that there is no other cases where we can find symplectic resolution. That question was answered by Kaledin, Van Sorker. They proved that there are no other symplectic resolution. So that's the status of knowledge in maybe around 2010 years ago, maybe. And what did I do? About this time, I also worked on this symplectic singularities. Before Kaledin, Len, and Sorger, maybe about 1 week earlier, we proved this for the case of rank 2. Rank 2 case, we proved this by a very different method. Rank 2 case, we computed something called string E function. Of the moduli space MSS, moduli space of semi-closed sheaves, and then we track that the string E function cannot be a polynomial, which means that there cannot be any prepend or symplectic resolution. So, and about a week later, this paper of Kaledin, Len, Sorger appeared, and by a very different method, they proved non-existence for much more for arbitrary rank cases. And also, I computed the string E functions for modular Higgs bundles, intersection cohomology for modular Higgs bundles, and so on. Quite recently, our computation was used by Maori and Miori for very interesting correspondence called Hodge singular correspondence for modular Higgs bundles here. Anyway, so that's the point when I stopped thinking about symplectic singularities, about 2010. But why did I stop? Because I was not happy with this status. So I wanted to know this question. So I secretly believe that there should be a different world in which there is a symplectic resolution of MSS in a different world. So I know that in the world of classical algebraic geometry, in the world of classical algebraic varieties, algebraic schemes, there cannot be a symplectic resolution, but maybe there is a different world where you can really find something like symplectic resolution. Okay, so that was my complaint, and that was my hope at that point. I couldn't think of any clever way to answer this question, so I stopped thinking about this problem, and then I moved on with the homomorphism theory and so on. Okay, so nowadays I think I have I got some new insight in this direction. So how should we look at this problem? We should look back to Bucknell's work. find an answer in a new world, in a different world. Right. So the slogan was that if your surface is symplectic, the moduli space inherits the symplectic structure. But what is a symplectic structure in Mukai's work? Suppose you have a point in the moduli space of stable sheaves, and the tangent bundle, a tangent space of moduli space at the point F, as is well known, is given by x1 of F on the structure sheaf of the surface S. And Mukai's symplectic form on moduli space MS is given by the composition of these maps, x1, ff, x1, ff, and you apply the unit of pairing, x2, ff, and then you apply the trace map to H2OS. Up to this point, it's completely general. You haven't done anything. But here comes the key point. You apply the symplectic form of the surface S, and then you get a map isomorphism to H2 canonical line bundle of S, which is just this is how we get a symplectic structure. The key observation here is that we didn't use actually symplectic structure. We used actually Calabi-Yau structure. So I think so. Here we use this isomorphism. Here we use the isomorphism. OS is isomorphic to canonical line of S. We haven't actually used the symplectic structure. We used Calabi-Yau structure here actually. So I think the correct slogan now should be something like, if your surface is Calabi-Yau structure on S gives you symplectic structure on moduli space. I think this is the correct point of view for symplectic geometry of moduli space of sheaves. Indeed, this is the case. By the groundbreaking work of PTVB, Pantef Toen, Bejosi, and Vaki or something like that. So indeed, this is what they discovered. So suppose Y is any Calabi-Yau default. This means it's a smooth projective variety of dimension D, which comes with the Calabi-Yau structure, meaning that you have an isomorphism structure sheaf with the canonical Y with the canonical line bundle, which is just half exterior power of. Suppose you have a Calabi-Yau default, and let's say M is the moduli stack of vector bundles or sheaves or G bundles, whatever, or G bundles, sheaves, or even perfect complexes. It's complex of vector bundles. Okay, and the little catch is that you have to think about is a derived enhancement. So I don't want to talk about derived algebraic geometry here because it's going to take some years, some days. Let me just say that derived stack means that for ordinary scheme theory or stack theory, you're applying your local model is a spectrum of a commutative ring, right? But in the derived world, commutative ring is replaced by or generalized by commutative differential graded algebra. Your ring comes with a graded structure and also comes with differential. So your ring is enriched with more structures. That's what I can say. And also derived in the derived world, the sheaf of Kähler differentials, the role of sheaf of Kähler differentials is replaced by the cotangent complex. You have to always use cotangent complex. When you're thinking about differential forms or when you're thinking about other things, symplectic structures, you have to use cotangent complex instead of Kähler differentials. Okay, so if you're not familiar with the derived world, derived schemes or derived stacks, think of it as an ordinary moduli space together with some decorations. Okay, so what do they do? In the derived point of view, the moduli space of G bundles or perfect complexes is the same as mapping stack from Y to the classifying stack of G bundles. Or in the case of perfect complexes, there is a stack of perfect complexes. So think about the stack of a mapping stack from Y to BG, or a mapping stack from Y to perf. So if G is reductive, then BG comes with a natural symplectic structure, but not ordinary symplectic structure. It comes with two-shifted symplectic structure. The same with the perf. Come with two-shifted. I don't want to talk about shifted symplectic structure, but it's okay. So one line is that one consequence of the distance of shifted symplectic structure, two-shifted symplectic structure, is that tangent complex of BG is isomorphic to the dual tangent complex shifted by 2. So tangent complex, cotangent complex are all complexes. So this guy, the right-hand side means that you think about tangent complex and shift every term to the left-hand side by 2 units. Yeah. So and then you do this, you do the usual stuff. So you think about the product of M with Y, and then consider the evaluation map to BG or perf. Just because it's map space, you can think about the evaluation map, and then you can also think about the projection map. Okay, so as I said, we have a symplectic form on BG, symplectic form omega on BG, and then I can pull back by the evaluation map, and then push it down by pi. So push down by pi, which means that we are integrating over Y. So for this integration, you use the Calabi-Yau structure. So then you get a holomorphic 2 form on M. It turns out to be a symplectic structure. This is 2 minus T shifted symplectic structure. Right, so what does it mean for the surface case? So when dimension 2, we're dealing with Calabi-Yau surface, in Paris case, then it means that the moduli stack, derived moduli stack of sheaves or vector bundles or G bundles, this guy has 0 shifted symplectic structure. So a consequence of this is that if you think about the open subset of stable sheaves, because this guy is already a smooth scheme, this is a smooth scheme. This is a smooth symplectic variety. So in the smooth case, the smooth scheme case, zero symplectic is ordinary symplectic. So this theorem covers quite work, and then we can think of the stack of semi-stable sheaves. This can be thought of as a classical truncation of the derived stack of semi-stable sheaves, and then we have a coarse moduli space map, SS. And this guy comes with zero symplectic structure. So PTVB, according to PTVB, this can be thought of as a symplectic resolution of MSS, the derived world. In what sense this is smooth? Derived sense. Derived sense. Derived sense. Yeah, in the derived algebraic geometry, we remember everything. Locally, it comes from a smooth variety, and you remember the defining equations. So, in some sense, in the philosophy of hidden smoothness of savages. So, surprisingly, it's classical truncation. Classical truncation. This is derived scheme, derived stack. You take out the derived structure, that the ordinary algebraic stack. Then you take the coarse modulus. Right. So, and quite surprisingly, I find that it's not, this zero symplectic structure has not been much studied so far. Somehow, I couldn't find properties of a scheme or a stack admitting a zero symplectic structure. What can you say about this? So I think I want to explore this direction in the future. But instead, what I want to talk about in the remaining minutes, I want to talk about the higher dimensional case. So when d is greater than or equal to 3, then this shifted symplectic structure is essential. It's very useful for sheaf counting in the Donner's Thomas theory. Okay, so let's think about the Calabi-Yau-3 case first. So now MS is the moduli of stable sheaves on Calabi-Yau threefold, fixed Calabi-Yau threefold. We fix an ample line bundle, which is general, and then we think about physical stability, and so on. And by the work of PTVB, this is -2 shifted symplectic structure. I think this guy is -2 shifted symplectic structure. Sorry, -1. P -3. And there is a work by Brab, Bussi, and Joyce, which tells us about the local structure of derived scheme with a -1 shifted symplectic structure. It tells us that if you have a -1 symplectic scheme, this should be locally, Zariski locally, critical locus of a regular function. So it means that your moduli space MS has open cover, statistic open cover, and each of the open set is the critical locus, meaning the zero locus of the differential derivative of a homomorphic function inside a smooth complex manifold and a homomorphic function. So moreover, this chart gives us compatibility, these charts satisfy us the compatibility conditions. So as a consequence, so first I should mention that up to this part, you don't need the derived algebraic geometry. You can actually, for sheaves, if you're only interested in moduli of sheaves, this result can be proved by gauge theory or elliptic partial differential equations together with remote Chern-Simons quotient. Think about the space of all connections, and then think about the curvature, the differential equations, the curvature equation, and then you take the slice slice with respect to the gauge group action. Then we restrict the homomorphic Chern-Simons function to the chart, and you get a finite dimensional model of the connection space. That gives us the local charts. Anyway, but for G bundles or for perfect complexes, it's really difficult to prove the same by using gauge theory. So with Jun Lee and I could do this with the gauge theory, prove this with gauge theory, but we couldn't do it for two-term complex cases. Already for the two-term complex case, the problem becomes too much complicated. The differential equation becomes very complicated.
What's the role of this function?
You will see. Just 1 minute. I'm going to talk about this. So this homomorphic function gives us two things. First of all, the tangent bundle of the smooth variety P alpha, complex manifold, restricted to U alpha. The cotangent bundle of V alpha, restricted to U alpha. You have the map, which is the Hessian of the function f. This is a two-term complex of locally free sheaves on U alpha, and because of the compatibility condition, this guy glue to a derived category object over moduli space M. Glued to a derived category object, but from derived algebraic geometry point of view, this is just the cotangent complex of the moduli stack, restricted to the classical truncation, which is a derived category object. Derived category coefficient sheaves. So obviously this is symmetric. So this is something called this object is something called symmetric perfect obstruction theory. And by the work of Berendt-Fantecchi or Berendt, get a virtual fundamental class. And because this is a zero-dimensional model class, you can find the number of points in the cycle. That's the Donat-Thomas invariant of the Calabi-Austin. Right. So that's good. But we can do more with this. For Donat-Thomas invariance, for this number, we don't need this derived algebraic geometry. But if you want something more, we need the structure. So based on this, now 5 authors again: B, B, D, J, S. Prof, Ulsan, Dupont, Joyce, Zendroy. Yeah, these 5 people. What they did is following. So if you have a homomorphic function on a smooth manifold, then you can think about the probable sheaf of vanishing cycles. So this is a purple sheaf of vanishing cycles defined on the open subset U alpha. Purple sheaves are like sheaves. You can glue purple sheaves because even though it's a complex of sheaves, it behaves like a sheaf. And what they track is that these glue to a purple sheaf. Let's say P. The abelian category of purple sheaf. Right. So, so that's a good thing about this function description. Think about purple sheaf cycles. Glue these. Right. So if you have a purple sheaf, then you can think about hypercohomology. Purple sheaf on MS. And this is something called homologicality. Because if you take the Euler characteristic of the cohomology theory, you get back to the Donaldson-Thomas invariant. So this cohomology theory is a refined invariant than Donaldson-Thomas invariant. So using this, so for the sheaf case, we could prove the same. Me and I could say the gauge theory anyway. And then after this, Lee and myself proposed that you can use this to define the Gopa-Kuma-Buffer invariant. And this idea was further developed by Molik and Toda. It's what? Refined. Refined, yes. It's also refined. And the conjecture is that this, the numbers defined in this manner should give us all. Right, so that's the development about DT3 using this derived structure, derived symplectic structure here. Okay, so I have 3 minutes. I have 5.
Yeah.
Okay. Then let me move on to the 4-dimensional case, which is very recent and which is still developing. So now we move on to Calabi-Yau 4-fold case. So now my moduli space MS is the moduli of stable sheaves on a fixed Calabi-Yau 4-fold. So by PTBB, this comes with -2 shifted symplectic structure. Okay. Then again, I can look up the book, the paper by Prof, Bussy, and Joyce. They worked out the local structure of derived schemes with -2 shifted symplectic structure. They tell us this story. So now the moduli space should be union of open subsets, that is the open subsets. And this U alpha is actually zero locus of a section S alpha, where S alpha is a section of a vector bundle F alpha over. Okay, this is going on. Maybe I should draw a diagram instead of this. This is the zero locus of a section inside V alpha. This guy is smooth. And S alpha is a section of vector bundle. This guy is not just a vector bundle. This comes with orthogonal structure, orthogonal vector bundle. And you have a section S alpha. And this section should be isotropic section. Okay, orthogonal means you have a symmetric bilinear pairing which is non-degenerate. S alpha squared is equal to 0. Okay, so that's great. So what this implies is that we have 3-term. This gives us a 3-term symmetric obstruction theory. And then, so 3-term obstruction theory so far, up to this part, you can work out by classical algebraic geometry. Don't need the derived structures. But you cannot get the following. So up to this point, it's completely classical. We can work out the same with the classical geometry. But you need to get a perfect obstruction theory, to get a virtuous cycle, you need this condition. The normal cone of U alpha inside V alpha should be contained in F alpha restricted to U alpha, and this should be isotropic. this isotropic condition cannot be, I don't know how to prove it classically. I don't think it comes from classical algebraic geometry. But from the other algebraic geometry point of view, from -2 this symplectic structure is completely automatic. So your normal cone is isotropic cone. And then in this setting, Jung-Seok Oh and Richard Thomas constructed a very nice homology class called virtual fundamental class. And then by integrating homology classes against this homology class, we get the four-dimensional Thomas invariant. So allow me 1 more minute. And what have I done in this direction? So actually, my student did more in this direction. So my student Hyunjun Park, he proved a fundamental result about four-dimensional Thomas invariance. The fundamental result is that the Thomas invariant is deformation invariance. Somehow, for ordinary DT invariance, the deformation invariance is automatic. If it comes from perfect obstruction theory, then deformation invariance is almost automatic. But in DT4 case, you have 3 term symmetric obstruction theory. It comes from autonomous construction. It's not automatic. You have to really prove it, and it requires certain assumptions. It's not automatic. This is a new feature, but anyway, it proved deformation invariance or DT4 invariance under some assumptions. It's not automatic, under a reasonable assumption. Right, and then he also further proved the virtual pullback formula. So meaning that we have relativized the construction of virtual fundamental class. Suppose you have a motion between derived algebraic stacks, and suppose the relative cotangent complex gives us has this minus to shift this symplectic structure, then we can define relative version of the autonomous theory. And then together with Hyunjun, we proved cross-section localization, and moreover, reduced DT4 invariant. Like in the case of Gromov-Witten invariance of K3 surfaces, the Gromov-Witten invariants are 0 for K3 surfaces, but you can reduce the invariant and that gets a reduced invariant. Like in this case, if there is certain forms like 3-1 forms, the DC4 invariant is already 0, but you can define reduced invariant. And A and Ko and Park, they used this Thomas for four-dimensional DT4 Thomas invariant to study a very interesting problem related to variation of particle conjecture, which is about forming a surface inside a labial hole. Okay, so I don't have time to talk about questions. Okay, I'll stop here. Thank you very much.
Thank you, Professor Kim, for the very interesting talk. Any questions in the audience?